this SIW is an combination of both waveguide and substrate. Okay, so this is what we are going to design today. So whatever you design now, first thing, you must know what is an application, what is it actually for. That's why I give this much of a brief introduction about CSIW. Okay, and okay, this is in second slide. You can see here, no, these are L, S, C, X, Ku. We know what is in frequency, right? That is the frequencies, number of cycles. We can use it in AM and FM modulation. Everywhere we can see the frequency, but it's a new term like S, L, S. What is that? That is actually a band of frequency which is introduced by an RF peoples. Okay, so that frequency, I can say, definitely say the frequency is a very important specification. Whatever you're designing, if you are designing an antenna, or whether otherwise you are designing one microprocessor, any product, it will come as a product in a real time. It will be definitely that frequency is a main specification. That's why I'm intentionally place this as your first slide. So you can see here L is in 1 to 2, that is 1 to 2 gigahertz coverage is L band. If 2 to 4 means that's S band. I think I don't know how many of you peoples or from students or staffs are taking that is in satellite communication as elective subject. In that you can see that uplink and downlink frequency for satellite communication. There you can see that C and S as an uplink and downlink frequency bands, which is used for a satellite communication. Yeah, this is what the frequency is. Okay, L to D. Yeah. I think how many of you know about what is a frequency range for a microwave? Microwave frequency ranges are from 3 to 300 gigahertz. Okay, but we can here you can see up to D only. Yeah, that is frequency. I can say about the frequency. You can see here is an higher frequency. This is an lower frequency. So wherever I go as an a speaker or anywhere, no, at the time I usually spoke about more about the frequency to the people or in staffs or any students, because it's very important term to know about what is the difference between frequency and also a wavelength. Yeah, if I ask you what is the difference between frequency of wavelength, your people definitely say that is an inversely proportional, that is frequency and lambda, that is in the wavelength is inversely proportional. Yeah, whatever you study now, just study with an example, it will be just fixed in your mind. So I will give you a short example for wavelength and also a frequency. Yeah, take it as an example. If you are walking, no, if you are walking for some distance, how long you are taken a step, one for taking one step, how long you're taking your leg to make one step, how long, that is a wavelength. How many steps, that is a frequency. This is a simple example. Okay, here you can see here, from here to here it is one step. How long, this is wavelength. How many steps I am taken to reach my destination, that is a frequency. And yeah, just enter into the 5G. Why 5G? How many of you people know what is the frequency which is used for our latest 4G LTE? Definitely no one answer, because they have to raise your hand, because this is not a visual communication, right? So I'm answer, that is in 2.45 is a frequency which is used in 4G. What about the 5G? What is about 5G? 5G, you can just frequency that is allotted for 5G is actually the two bands. Okay, if you see here, that is two bands, that is lower band and also an higher band. Two bands of frequency we can use. Yeah, this is two bands of frequency. That is lower sub band is about 6 gigahertz, up to 6 gigahertz. That is above 2.45. That is from 3 to 6. That is a sub band, lower band. And here you can see that is 24 to 100 gigahertz. We can make an antenna for 5G. But People at Samir, na, they are actually make an antenna at 60 gigahertz, but there is more and more of harmonics will affect the antenna's parameters. So now in India, they fix with 28 or 28.5 or 27. This is what the frequency which fixed in India on 5G. So today we are going to do it in 30 or 20 to 30. Okay, that is a higher in frequency, though definitely this is, I think, in the first session, Gulam Nabi sir said about a millimeter wave antennas. That is a theory about millimeter wave. Now these come under millimeter wave. Yeah, what is the main advantage of 5G? Definitely, what is in now the speed of 4G? I think it's actually about 300 Mbps, but no one get it is in 300 Mbps. Everyone will get a speed about 100 Mbps only. So the main aim of the 5G to get the speed of about 10 Gbps. Just think about the speed. If you are downloading one movie, na, it takes about a hour or some. Nowadays, it's take about 15, at least 15 to 20 minutes. If 5G comes now, it will be taken only 5 to 10 minutes, because the speed, just think about the speed is 1 gigabits to 10 gigabits per second. Yeah, another advantage is definitely a bandwidth. I can give another example to understand a bandwidth, right? Usually the bandwidth, how we define, f2 minus f1 at the higher frequency minus a lower frequency, that is an actually L bandwidth, right? The main application, that is a main advantage of 5G is it will give a higher bandwidth. Then what is in bandwidth? I will give an example. If you consider the theater, no, there is an opening like an exit and entry. At the time at 1 second, no, at the time, how many number of peoples will enter inside that gate? That is actually a bandwidth. Yeah, that is how many number of users can accommodate in case of this antenna and communication. Now how many number of users may use one base station at the time? That is what the bandwidth. Main aim of a 5G is to increase the bandwidth. That is number of user may increase. Okay, and yeah, another thing is MIMO. What is MIMO? You can study in communication systems, I think so. MIMO is multiple input and multiple output system. Yeah, this 5G is come under a multiple input and multiple output system, because there is nothing in a single one antenna can place in that base station or in our mobile station. It can an array of, that is not a MIMO, that is a massive MIMO will be there in a 5G application. Yeah, that is massive. If I start about the massive MIMO, that is a separate session. That is a big drawback. That is a very difficult to fabricate or to design this MIMO system. That is what researchers or researchers main burden is this MIMO. And another thing is the need of an eye gain antenna. That is the first and foremost thing. If you are designing an antenna, if you are staff or anyone, no, if you're giving a project like you are going to design an antenna, the first thing you should search in the web is what are the types of an eye gain antenna. Now this SIW, no, this is actually the eye gain type of an antenna. Yeah, you can see here now, usually the gain, what is the gain? You can see this here, dBi. This dBi stands for decibels with respect to this I is respect to, that is isotropic antenna. Isotropic antenna is actually an imaginary kind of an antenna that is not exist in this world. But because if you designing an antenna, it will start radiating in one direction or in bidirectional or in n5 direction, like that now. But this isotropic antenna will radiate equally in all the direction, equally. But that is not possible to design that kind of an antenna. So this taken as an isotropic antenna as a reference antenna. So if this is my radiation pattern of my isotropic, that is reference antenna, this is an actual radiation pattern of my antenna. So what is my gain? This minus this. So this is what my gain of my antenna. So I need an eye gain antenna for a 5G application. So SIW is one kind of an eye gain antenna. There is some another kind of an antennas too. If you see the Vivaldi, these are kind of, that is a type of antennas. Yeah, this is what the SIW. Okay, at the first time if you see another can't able to see what is this, it's like just like a plate, but yeah, this is what I said. This is usually a patch antenna. You can study in antenna theory, I think so. If anyone say, they can just recollect it. Yeah, it consists of a ground plane. Ground plane is a conductor. You may use a copper or aluminium or otherwise gold also. If you are very well no, well off, you can use a gold also, because golds and all no, that have a high conductivity. So gold. And then dielectric substrate, there is a lot and lot of dielectric substrate which is available in our industry. You can use the skin is also a dielectric substrate, water is also the substrate, paper is also the substrate, but availability matters a lot. Nowadays most available dielectric substrate is FR4. Okay, so again, the top layer is a radiating element. No, never say this is a patch. That is an actually a radiating element in case of a patch antenna. That is also the conductor. That is also the copper or aluminum or whatever it is. This is an actually a patch, right? Yeah. Then what is this? This is actually a waveguide. You can see in our communication that is an antenna and waveguide that is in microwave lab. This is a waveguide, right? It's an This is an actually 2D one, this is an 3D one. It's like a object, this is like a scale, just like a single layer. Okay, so combination of these two becomes this SIW. You can see here, same dielectric material at the center, ground plane, that is a conductor, top layer is also a conductor. Yeah, what is this one? This holes now, which is buried in this patch. If you place the holes which buried in this patch as an side walls, it became, yeah, what is that? It became an SIW. Yeah, yeah, just some brief introduction about it. Yeah, you see, this is a rectangular waveguide. See this rectangular waveguide which is surrounded as a four sides with the metal wall. So just to think about this substrate integrated waveguide, it consists simply a ground plane, that is a conductor. Yeah, that may consider as a wall, and top layer is also contain wall. Then what about this side? Two sides. So to make the wall at the sides, we may need to put the vias. Vias you can study. I think you may study about the, if you place an vias, that makes us a wall at the sides. Okay, that vias are buried in the substrate. So at the first time now, if I hear about this SIW, what is the thing which strike in my mind is, if I feed this, no, the waves which are escape from between these two wires, right? This is what the question which raised in my mind when I was ME. Yeah, later on I found that vias na, there is a metal conductor that is also filled with in copper, so it makes some magnetic loops between these two wires, so that magnetic waves doesn't allow any electromagnetic waves to escape out from this box, that is this substrate. This is what simply SIW. And if you consider what is an advantage of using this, that is what now, if your PCB also giving the same thing, then what is an advantage in this SIW? That is what's the main question. Why we are doing this in a different technology, that is an SIW technology. That is, in every thing there is a losses, right? Losses is there. Yeah, the same thing here, we can able to control the loss. If you see the dielectric loss now, dielectric mean by selecting a good conductor, that is a good dielectric material, like an higher epsilon or material, that is a dielectric constant material like 10.4. For normally in FR4 we can able to give only a few dielectric losses we can able to reduce, because that epsilon or is only 4.4 there. So if you go with a higher dielectric constant like a 10.2 kind of a thing at that time now, you're able to reduce the dielectric loss. Another thing is radiation loss. Radiation loss, if you're placing these two wires very closer now, no electromagnetic waves are able to escape from this board. So at that time you can achieve the radiation loss. That is reduction in radiation loss. And yeah, this is what an actually SIW is. Yeah, this is a side view. See, this black color one is a conductor. That is a ground. Ground means bottom wall. And this black color one is an top wall. This is a side walls on both the sides. This is actually a vias. Vias means nothing. That's a holes. Holes that is put in, like if you are emming something, some cotton wools, na, at the time, there is an the thing to put a hole, right? The same thing here. Or otherwise, if you are punching your paper with a puncher, it's a kind of a same kind of a thing. If you see here, this is our holes. This is actually a top view. Okay, the things to be considered to design this, because today we are going to design, not only it is not a theory part. Why I'm insisting this theory is, before whatever you designing, you must know about what you are designing, right? So that is why I'm very insisting about this theory part. So today we are going to design, right? So at the time, what are the things to be considered while you are designing? That is, what's your diameter of your via, and what is the spacing, that is a center to center spacing between the vias, and what is the width of the via. What is the width means, you no need not to be measure this width, there is this end to end. Width should be between this whole center to this whole center. Okay, yeah. Then what is this? Instead of using vias, no, if you are going for vias, that is an SIW with vias for fabrication at the end of, after the simulation and everything, if your project is success within simulation, definitely the next step is a fabrication to make it as a product, right? At the time, if you are going to put a vias, the cost of this becomes very high. That is why I give some other replacement for, instead of vias, you can put stubs here. This is actually a stub black thing. Instead of vias, in place of vias, I make stubs. Here also the same thing. What is the length of the stub means length and width, which replace with diameter of a hole. And spacing, the same thing, the spacing between the two stubs, the same thing here as a width. Width you consider here as a this end to this end itself, because we have attached some separate part of a stub here, no? So that's why. Yeah, now we are entering into antenna design. What is the first thing? Specification. I said about the specification, right? The first thing, because most of the people I think of from final years, you may do your project in antenna field also. If your guide or anything, if you are selecting an antenna as your domain, the first thing which strike in your mind is a frequency, which I already said. First, fix with the frequency, and second is a size. Why I'm giving a size here? Because if I place, for example, if I am giving 2.45, which is for a mobile application, that isn't for ISM band, right? ISM band. For ISM band, I'm able to make a different kind of antennas for different size. So first thing I want to know is size. What is the dimension of my antenna? What is the type of an antenna I'm going to design? Because in this world, no, there is a lot and lot of type of antenna. You can able to design a non antenna in 2.45, and also the PCB antenna in 2.45, and sheet antenna or wire antenna or dipole antenna, many kind of antenna in the single frequency. So first you have to fix what kind of an antenna, what is the space which is available to place an antenna, and size. That is what I said. Size and dimension are interrelated. And material, yeah, there is lot and lot of things to said about material. Is take a day actually, because a material selection is a very important thing. Yeah, I already said, and the first slide, in the introduction slide itself, I already said why the material selection is important. If we go with an 5G application, at that time we need to select the higher dielectric material. And also because if you are selecting a lower dielectric material like an FR4, because FR4 is a cheap one which is exists in normal rich street also, but high dielectric material you can never find in any rich street or anywhere. You need to put the order to abroad like that. Yeah, but the thing is, if you are doing that your 5G antenna in FR4 na, that may melt and doesn't give a good result. That is like a dummy antenna, never use in like a product. So we can go with a higher dielectric constant material like Teflon is also not a good material. You can go with the Roger ortidurite. The other name of that is an ortidurite. The dielectric constant of ortidurite is about 10, I think so. Yeah, the reason is now why I'm insisting. I don't know how many of you are aware about dielectric constant of a dielectric material is very important to be considered while designing one antenna. And then how you feeding the antenna? Because if I made an antenna, okay, I'm going to place in my base station means on that big towers or placed inside near our homes now. At the time you are going to place your antenna there, simply think about it. You need to think about how you are feeding that antenna, right? I think people who studied antenna theory may know about what are the types of feeding available. Okay, or otherwise in second session I think you people may had an hands-on session on patch antenna for millimeter wave, right? So at that time you are giving some feed. I don't know what feed they are giving, maybe an insert feed or a simple strip line feed. That is a kind of feeding for an patch antenna. Okay, so you may select what kind of a feeding. It depends on placing your antenna, where you are placing your antenna. Just think about wearable antenna. If you are think about wearable antenna, you are going to place it in your gene or anything. At all the time, if you are feeding your antenna with some wires, na, you are walking. If you are walking, that wire is also, that is, and feeding is also come with you. So at that time, you need to think about what kind of a feeding you are going to give at the time. Okay, at the it depends on the placement where you are placing. And then SAR. In case of an wearable, definitely the SAR. SAR is specific absorption rate. I think many of people may aware of about this because I think most people may stop endearing to that is an 2.0. The big issue is what, the frequency, right? The same thing, that SAR is, and why that birds are died because of a SAR, that is high radiation. So our government will give some regulations for emitting a radiation, but no one at all, any user, no one will stick to that regulation. They are giving more radiation to us. That's why infertility and birds and everything no, gone. So if we are an engineer, no, we need to think about this SAR, that is an radiation. And then S11, that is in written loss. These are come under that parameters. After designing, you can see the parameters like an S11 and VSWR. And then radiation pattern, whether it is in bidirectional or directional gain. From the radiation pattern, we are able to get what is the gain of an antenna and everything. Okay, this is what the specification. And then just note it out. If anyone interested to design it again, this SAW after I'm designing, now if you want to try it, please to make a note. Okay, or otherwise I will send this PPTX to your coordinator. You can get it from them also. This is what actually in design equation. Design equation, that is in first is FC. This is in frequency of operation. If you are placing the frequency of operation, what is your C is the speed of the light, M and N is a number of modes. I think you may aware of the modes of operation, that is T10, T01, T11, TM, transfer electromagnetic mode. There is a types of a mode is there. So you can get it FC, and EAD is a dimension of these things. Because you can see that and another thing, you can see the waveguide in our lab there. You can see it from one side, it's a, like a hole, like the centrally it filled with the air only. Then how it is no it is compared with an PCB board? Because air is also one kind of an dielectric, right? That is also one kind of an dielectric material. And also there is another waveguide is also available in a market, that is a dielectric filled waveguide. The center part is not vacuum, it is filled with a dielectric substrate like a Teflon or Rogers. Yeah. Okay. And AS is also the width between one hole to another hole. This is so called width here. And here you can see D is a diameter. But everything can see here, no? Everything depends on lambda g. What is the lambda g? That is a guided wavelength. That's why I insist the frequency and wavelength is very important to design an antenna. So lambda g is a wave, guided wave. Depending upon this guided wave only, the length of this SIW defines. Yeah. This is what the specification. No. Frequency is 20 to 32 gigahertz. I already said the bandwidth is a main thing. Yeah. This SAW gave wider bandwidth. Like my SAW will work from not from 20, it may work from 15 to 32. Due to that RAM space is not very less in my system, because it need a supercomputer at that time in system, I make it as a small thing. So 20 is 32, 20 to 30, 20 to 32 gigahertz my SAW will work on. If you see, the simple antennas will work at a resonant frequency like 2.45 or otherwise 224 or 225. There is a wider band or ultra wide band. This SAW will give a wider band. Here, yeah, what is in my H dissipates here as height of my dielectric material. Here I selected material as a Roger 5880. That is an RT duroid. And my ground and patch. That is not a patch, that may be in a top layer in case of RSIW. In case of a patch, it's known as a patch or radiating element. Here I can select ground and patch as a copper. So Roger, I said no, it's 4.4, I think so. It we have 4.4. Height is 0.8. And also the main thing, no, just like that, we are not able to put a height of a dielectric constant. It is an only available in some four heights. Like an, point 0.2 is available. That is also very difficult to get in market. 0.8 is available. 1.6 is available. 2.2 is available. This is what the heights that are available in a market. That is left for an, any dielectric. To get a Rogers is not a good easy task. Yeah, if anyone or any staffs are doing projects in this Roger material, na, that is in your PhD work in Roger material, that is not an easy thing to get and find this Roger's blade 0. Yeah, this is what the design consideration for that stub. I said not stub at that. This is what the stub I said, no. So now I am going to give an design consideration of these stubs. Yeah. S is a spacing between the two stubs. L is the length of the stub, single stub, width of a single stub. This is a conductor and a substrate and dielectric material have some widths. No, this is what the length is 7 mm and width is 22 mm. Yeah, let's start our CST session. Today I'm going to design. There is a lot of softwares are available to design an antenna or a coupler, whatever. This CST is easily available in our website, and also in the student version is easily available in OpenNet. That's why I chosen this as a platform. Okay. Yeah. First, I will give a simple introduction about the software, and then we will move on to. Yeah. You need to, in student edition, this is what the first thing which appear in your, if you are clicking on the icon of a CST and able to see these things. Yeah. Need to give a no here. Yeah. The first and foremost thing, this is just an introduction about that software. First thing, you need to click this new template, start loading. These are the platform which is there in the CST, that is in microwave or of an optical. You can design the microwave products here, and or of an optical products also here. This EDN electronics which is used for the electronic, there is some short circuit in a PCB boards now. We can able to detect the PCB boards here. Here you can see the TMC EMI, that is for electromagnetic compatibility. If there is an interference between any product, you can detect in this with this platform. This particle dynamics and the static and low frequency which is used by and mechanical peoples. Yeah. Now we need to select this microwave and RF opticals. If you click this now, there is an again and brief platforms here. Here this is an antenna. If you want to design an antenna, you need to click this. If you want to design some circuits or a components like a coupler, you may, I think you may, people may see in microwave lab, there is a coupler, there is an hybrid coupler, 3 dB 6 dB hybrid couplers or a filters can design using this platform. At the time you need to click this. And if you see need to design one radar which is for a multi application. In radars now, at the time you need to see the cross section of a radar, because radar which is mainly used to detect the objects which is around you. At the time you need to click this radar cross section. And this platform is for biomedical application. We are going to design a biomedical application products, because we need to see SAR at the time, right? So at the time you need to give this biomedical application. For optical application, you need to select this one. This periodic structure is mainly for and phased array system, because I think most of the people now are moved to for phased array system. That is also one kind of an high gain antenna and beamforming antenna for 5G application. If anyone plan to make a phased array, you need to select this periodic structure platform to design. Now we are going to design antenna, that is an SAW. So you need to select this antenna, then click next. Yeah. If you see here, no, if you want to design an horn antenna or cone antenna or waveguide, simply a 3D antenna. If you want to design a 3D antenna, 3D na, that is an object, 3D object antenna. Na, at the time, you need to select this as a platform. Because why I'm giving stress of different platform now, if you are designing the waveguide in this platform, it definitely doesn't give a good result at that time. So because different platform has a different type of meshing and different type of an algorithm which is running backside. Because this software, any software, the background is an algorithm, right? So we need to select the correct algorithm and a correct platform to get a good result to overcome a good product. So the second thing, and second thing is for a planar or patch or slot. Okay, if you want to design a patch antenna, like patch means our PCB antenna. This CSIW is also come under this planar one. If you want to design a wire antenna, you need to select this. The spaced array and unit cell analysis, you need to select this one. Phone antenna, or if you need to integrate two antennas, at that time you need to select this. Reflector means you can see in our homes now, that is a satellite dish antenna which is used to receive signals for our TV communication. Now that is an actually a reflector. And dielectric resonator is one kind of an antenna. And also the RFID antennas you can see in toll gate, and also staffs, and we use that RFID tags, no, that is also contains some antenna to receive and communicate with the products. At the time you need to give this as a platform. Now select this patch Then click next. Here you can see time domain and frequency domain. So this time domain and frequency domain, this frequency domain you can see here na, for resonant antennas means you are designing some appropriate antenna which is work at center frequency like 2.4 or 3. That is for that antenna may work in only one frequency. If you are designing that kind of an antenna, at that time you need to select this frequency domain because it takes a lot of time to solve. Okay, and this is for wideband and multiband. Now we are going to design that wideband only, right? So we need to select this one. And here actually this is a student version, so that is an options are very less in this case. If you are go with an original version, at that time you can see a type domain solver. That is lot and lot of solvers are there. Multi layer, if you are doing a multi-layer antenna, at the time you need to select this multi-layer. Now I'm going to select this time domain as my form workflow. And please do note the dimensions in mm because I'm going to give my dimensions in mm and frequency in hertz. Yeah, if you are going to design your antenna in hertz and kilohertz, like a low frequency antenna with a high dimension, at that time you do need to give this hertz kilohertz. But now I'm going to design it in gigahertz only, and time is ns. Need to check everything and then click next. So this is what your solver, that is your solver you selected as time domain solver. This is what the dimensions in mm. You need to check these ones because after I made the antenna, you never this solver never allow you to change anything. So please to check it out. Here you can see that printer microstrip PIFA. Yes, what is the meaning of PIFA? If anyone know, this is a kind of an antenna which is placed inside our mobile phones. That is planar inverted F antenna. And slot antenna and spiral antenna monopole geometries, we can make it using this platform. And just give an example. Yeah, this is what my platform. Yeah, I don't know actually how many of you know about this CST, and maybe yesterday or day before yesterday session they may give this introduction, but it's before starting this I need to give this introduction, a brief introduction about this, then only it is easy for you people to design. Okay, and this is a home page. You can see the solver here. Now we selected a time domain solver. I'm not going to give a very brief introduction because it takes too much time. Okay, here you can see this is a navigation tree. Whatever you make, you can see in PSpice like that. You can make it in communication lab. Like PSpice is a kind of a software. At the time, you able to see the workspace there. In C also there is a kind of a workspace is there, and status bar is there. Right? The same thing here. This is a workspace here. Whatever you're doing, if you are running your simulation, it will come here. If any messages, no, it will appear here. And then this is a navigation tree. Whatever the objects you are adding in our workspace, it will appear in this navigation tree. If you are giving a
Excuse
ports,
me,
the
ma'am.
results is also. Hello. Yeah.
Ma'am, can you hear me?
Yeah.
Ma'am, yesterday only we had a CST Studio hands-on training, ma'am.
Okay. Okay.
So you may cut short the introduction, ma'am. Directly
Okay.
you may proceed with that.
Okay, sir. Okay, sir. That's what I need to know about.
Yeah,
That's why
yeah.
I said okay.
For the past 2 days, Tesla Minds engaged us with the CST Studio, ma'am.
Okay. Okay. So everyone is aware about the introduction part, right?
Yeah, yes, ma'am. Yes, ma'am.
Okay. I will start with my design.
Yeah.
Okay.
Thank you, ma'am.
Thank you. The first thing is a modeling. I think you may people have a good knowledge in CST designing because Jayanandan is also a good uh, one to design this in antennas in CST. So first thing, just click it out because the first thing we are going to make is as an ground, that is on bottom one. Okay, just press escape here. This is a bottom one, name it as bottom. I already said my width of my SIW is 7. Now I'm going to place minus 3.5 to 3.5 here. Why I am giving this minus 3.5 and plus 3.5 is totally it's 7, because my width of my antenna is 7. Because if you are giving, I'm able to give us a 0 to 7 also. Why I'm giving in this pattern is, if you are giving in this way, the radiation pattern will come at the center. At the time only you are able to see the radiation patterns in different cuts. Means or theta, that usually is a coordinate system, right? Or theta phi. If you want to see it in the different sides or different cuts, you need to give the dimensions in this manner. Okay, so 3.5, no need to give an that is in units, because already we defined here it's minus 11 to 11, minus 11 to 11, so totally that is 22. So here it starts from 0 to, this stands with width, and y is stand with, that is length, and here this is an height. Usually that conductors like in copper, aluminum, and whatever like in gold, it is available, the copper, it is available in the market with 0.035 mm. I need to select a material that is actually a copper. Copper annealed you need to select, because whenever in a fabrication center there is not a pure one copper, right? There is definitely, there is some losses in the material. You need to select this copper annealed and then load. Just need to preview it. Yeah, it's look like this. And okay, after this you can able to see this in component bottom. Again our bottom one is ready, and second thing is substrate. Yeah, same width and length, but height there isn't some different change, little changes in height. What is that? Minus 3.5 to 3.5. My y-axis is from minus 11 to 11, and my z minimum is from 0.035 to, actually I already said height of conductor is 0.035, right? I said now our height of a substrate is, I already said that 0.8, right? So I need to give here as 0.835, that is 0.035 plus 0.8, 0.835. And then I need to select a substrate here. It's not a copper, our dielectric material is different, right? That is Roger. Yeah. You see here, no? In Roger also there is so many variant. Roger 3003. We need to Roger 5880. Yeah, found it. 5880 law C. Load. Preview. Just like a sandwich. Ground and then substrate is above the ground. That is above the conductor. And you're going to make a top layer now. Same. Minus 3.5 to 3.5. This is again minus 11 to 11. And now this is from, it's like a sandwich, right? So when what is in dimension, we end with 0.835 to 0.835 plus 0.035, because our height of our top conductor is also 0.035. 0.87. Again, we need to change the material. We already loaded a copper here, so we can just select it from this drop box. Again, preview. Now we made a PCB. This is an actually a patch antenna kind of a thing. We need to make this PCB to waveguide. So for that, we need to put stubs at both sides. Just consider like in coordinates. No, you can see that coordinates like minus 1 1 0 0, like that, minus 1 1 1 1 minus 1 1, like that. No, there is a coordinate for this four, no, four cups. So you need to use that first. Now we are going to bury that stubs in top layer and bottom layer. We no need to disturb a center layer, so called a substrate. So again, select modeling, press escape, and this is a bottom right side stub. BOT bottom, or for right side stub. So I already said we need to select where we are going to put the stub. So this 2.6 to 3.5. Why this 2.6 to 3.5? 3.5 is my width of my substrate and my PCB, right? This end with 3.5. So I need to put a stub here. Okay. So 2.6 to 3.5. And my Y means it's from 11. Right? So minus 11. So 3.5. I made it wrong. 3.5 we need to put here. Here it's minus 11 to minus 10.4. Why minus 11 to 10.4? Because it's already, I said, it does actually four coordinates. Here minus 11 to plus 11. This is minus 3.5 to plus 3.5. Now I am going to place a stub in my right side. So same thing. Now height may differ. Why? Now we are going to place a stub at the bottom layer. So what is my height here? 0 to, excuse me, 0.035. Same, copper as our conductor. If you are viewing this with zooming this, I zoom the too much. You see here, you're able to see when this is a key which is used to rotate. You see here, no, this is what a stub. Back to our reset position. So this is what I need. Yeah, I made one stub now. I made it in the row. I make a stub here, 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 here. This whole corner I have to cover with the stub. I need not to place again, draw stubs again and again. I think you may aware of this. This is so called transform. This is used to copy our object. So translate it. I already said that is a spacing between the two steps is translate. Need to give here a copy. And where in which axis you need to copy the steps? In y-axis. So what is the pitch? That is a spacing between the two steps I already given in the PPT for design consideration of stub. That is an actually 1.2, right? So here the repetition factors give you how many number of oh, I need to cancel it. I need to select the stub one, stub alone. Please to select the stub, single stub. If you are selecting this one, this may become a transform one. So stub one, then transform, translate, copy, in y-axis. (1.2). Just something has happened. Bottom right stub. No, I need to select this one. That is what a mistake I made. Bottom right stub. Transform. Translate. Copy. Because what mistake I did was I selected the stub substrate here. I'm just confusing with that name. If I selected this substrate, the substrate that is the center part will be copying. So I need to select bottom right stub. That is what the name I given to this stub end. So spacing is 1.2. Repetition factor you can see here. No, I need only 16. No, 17 is okay for me. Okay, this is what the stub I need. So if I okay, this is what how many steps you can see. This is a easy step to copy the single thing. Okay, then again I want to make this step in my left side. So we are able to copy this the same thing, but we can make another one. Yeah, can say now that is bottom right stub. Yeah, now here there is a simple change in our coordinate. What is that? Need to place it in left side. So it became minus. So y minimum is minus 2.6. To y maximum is minus 3.5. And y and all same. minus 11 to 10.4. 0.035. Same copper nail. It's left side because already the name is there. Yeah, it present at the bottom. Bottom left stub. Now again, I want to it's a bottom right actually. I made now I'm going to copy the bottom left one. This is a left to us, right? So bottom left one. Need to transform this. Copy. Same thing. Spacing between the two steps is 1.2. Okay. Again, you need to give the same number of repetitions like 17. Ayo, I made it in very yeah. What happened to my system? Sorry for the interruption. I think something happened to my system. Actually, I didn't save. I think so. We need to design again. So ground everything. So what I'm going to do is can just I already made this for my reference. Sorry for the interruption. Actually, I need to do again because the system is crashed.
Okay.
It's 3.5, right?
Yesterday also the same thing had happened, ma'am.
yesterday also.
Yes, ma'am. With the
Yeah, the thing is because we are using the student version, right?
yes, ma'am.
Because they are giving some elements. I'm using a net also, internet. If you are using a CST, never use a net. That is what the biggest burden for us too.
Get this
If
problem is to get the licensed version.
yeah, because a licensed version is cost is too high. No,
Yes.
that's why it was only available in colleges. In SSN, it is available. In Samir, it is also is available. But at the time, I didn't face these kind of things. But after getting to this software, that is in student version software, there is a lot and lot of burdens. We can also see some errors during after the simulation also.
Okay,
So
okay,
that is what I think.
okay, fine. Yesterday's session was also postponed to later date, ma'am.
Okay. This is an I already made it, so no problem. We can make it. I will make it in a quick because we are not able to use the cracked version as this is an this is an internet platform, no. So if I am using the cracked version, I got caught by the CST people. So that's why.
Okay.
Actually, this is a that is a tip for the people who are going to be used in the future.
Design, design
At the time, they was because the students, na the time something happened to my project. The time because in my later days, by in college days, I too do this kind of things. Something happened to my project, so this is not a so better you can save it out. First, I just forgot to save it. The first thing I want to do is save.
Mm. Then and there you can save.
Yeah, at least up to these steps, it will be saved in your in our CST file, right? So it's 0.835. So again, it's a copper. Okay,
Yes, okay, ma'am.
please do use Control S all the time after making an each element. No, please do Control S pressing. Now it's right side step bottom.
Previously, you wrote BOT or step like that. You
Yeah, that's up to us, na. That's up to us. It depends.
there is no any syntax design for it, no, ma'am.
No. It's not like a C everything. Whatever you want to give, you can also give RST.
Okay.
Whatever. No syntax here, like in C.
That software understands whatever we need.
What? I didn't get you.
No, no, no. In whatever manner we give, the software understands it.
Accept because it's just a name, right?
Okay.
So there is no problem in it. If you are giving here now, if you are giving like, wait, need to give 2.6 now. If I am giving 2.6 na,
Hmm.
at that time it will give error because already we are selected.
Okay, fine.
So there is some so name and all no problem. Sometimes I gave my name too, no problem in that. 11 too because I'm going to now I am going to do it in this side. Okay, So that's 11 to 10.4. If anyone had doubt, no, please do ask. No problem. 0 to, because it's visual. No, if I am in there, no, at the time, for many people, many doubts may arise.
Yeah.
Uh, I
In
have to come each
we
place.
have
It's take us.
muted the participants.
Yeah,
Interference.
but this is actually very boring one year.
Yeah. Now I have made unmute option to all of the participants. They mean
Yeah, if they have questions, no, they may ask.
yeah.
Because this is not a simple patch antenna, that kind of thing. To understanding this concept is itself very difficult.
Only interactive sessions will provoke
No
the.
problem, no problem. At the end, I will answer for everything. Yeah, this is a step, right? So now transform, copy. Y-axis we need to copy. So spacing between these two is 1.2 mm. So again, I already said repetition factor is 17. 17. Because my length is this much. If my length is too much, I can make the repetition factor this till this end also. I made it. Okay. Left side stub bottom. So again the same thing, but with negative axis. Minus 2.6 to minus 3.5 because it is in left side. Again same 11 to minus 10.4. Here z is again 0 to 0.035. Copper, same material. Again, it will come at the bottom. Now you need to control S, press control S, or otherwise it may gone. Again, copy. My spacing is 1.2. My repetition factor is up to 17. Made it in our view. Preview it and then press OK. Now we made steps at the bottom. Okay, we need to add it, or otherwise at the time of subtraction it's a very big process. So I'm going to add these things. So it's a boolean operation, you need to select. Okay, now please do note, while adding you need to press control key and then select this every whenever it comes. No problem. If I double click it, no, it got opened. Now simply we may click the left. Simply control.
Can you try with the control and down arrow, ma'am? Will it select?
Yeah. And then go to boolean add. Now this is full left side bottom. Do the same for right side. Okay, boolean. For addition, this is different. For addition operation, this is different. The pressing of a control key is different. For subtraction, it is different. I will tell you how it is. Now you need to subtract these two from bottom. Okay, select bottom first. You are going to subtract this from this. So bigger one is bottom. Select boolean subtract. Now press control and left side bottom, and also right side bottom. Yeah, now you are able to see this, I think so. Yeah, at bottom end no, this minus from this. These are all holes. Instead of wires, I am placing this holes. So this is a stub actually. Actual stub is this. This is my holes, like in spacing between these stubs. Now I made a bottom one. The same thing I need to do it for
Top layer also.
top layer. So what is the change? What is the changes in this top layer? What is the difference I need to put while I made a modeling? Yeah, this is actually right side stub top, right? So right side mean definitely what is that? That is in positive. Need to put this in positive, right? So 2.6, same thing what we did for right side stub bottom, you need to put the same thing here. 3.5. So again here minus 11, right? 11 to minus 10. Everything relates to the coordinate system on this axis one. Now only changes is top layer. So top layer is a top conductor. We need to consider the top conductor. What is the height of a top conductor? Where it starts 0.835 to 0.87. Right. Need to preview this one. So actually at the top side, you're not able. Are you able to see this? Think.
Yes, ma'am. We
Yeah.
can.
So this is what the stub we placed at the top layer. Again, we need to do the same process. Right side stub top, transform, copy the same y-axis only. 1.2 repetition factor is same 17. You can 1.7. Okay, press OK. Will come, I think. Okay. Again, do it in left side. Left side stub top. What is the difference here? Minus 2.6 to minus 3.5. Y is minus 11 to, no changes in y actually, minus 11 to minus 10.4. The same z, 0.835 to 0.87. Copper, same copper. If you previewing this, it will come. So you need to make the transform again. So for that you need to select the left step at the top. If you double click on it, now it will open. So single click is enough. I made it a double click. So copy. So again y is 1.2. The repetition factor is 17. If you are previewing this much now. Now the next step is you need to add again left steps. Control 17 boolean add again If you're adding this now, it become merge. So be careful while selecting these things. Subtract, no add. Okay. Now from the top layer, we are going to subtract these two steps. So top layer, boolean, subtract. Now press control and select left step and also the right step at the top. What I made? Control Z. Something I made. It's a top layer, right? This is a left side step. We need to check that height. Already subtracted 5 7. This is what the mistake I made. This is 8 7. No, no one remind me why. Top layer, boolean, subtract, control, right side of a step, press enter. Yeah, done. We done with the simple SAW. Lot and lot are there to given. Yeah, this is what, and corrugated SAW. We need to give feeding and all. That may take time. So this is an actually simple thing. Yeah. No. Okay. So this is a top layer. This is actually the added step at the top and also the bottom. So these steps are act as a wall, that is in side walls. So here can see that top layer is in yellow color and bottom layer is yellow color. So top and bottom layers are there. Where is the side walls here? So this steps, no, it's here act as a wall, side wall. So we finish up with an SIW. It's simply CSIW. Now the second thing is, final thing is what? We need to feed this, right? Hmm. Zoom it, again zoom it, again zoom it to see this part. The small part, no? That is a top layer part. You need to select this one. So please to zoom. Yeah. Now you select this. So select to feed. This is for feeding, okay? Pick face, because this is a face, right? You can select the edge anything, but now I'm going to select the face for feeding. This red color one is a selected one, so just move it on it. Once this your desired part is came, double click on it. It's like if dots are come, it got selected. Then go to home. This is actually an easy thing. There is an actually what can I say, easy one to easy way to give and feeding. You can also do it in manual by doing here. There's an actual port, wave port, discrete port, plain wave port, but I need it in a simple way. Macros. First thing is I need to select pick face and face. Now macros, solver, ports, calculate, port extension, efficient. So here it gives like there is some while you are designing in designing is an equation in patch antenna, no, there is like some criteria is that w by h should be less than 10.1 like that. So it's not satisfied because our height is too small and 5.2 is our width, which is there is some criteria. So I think it is not built it, so the ports are not made, but usually now we made it like this. It's an easy one. So I made it in manual, but you can do it in this way. for an patch antenna or any antenna you're doing now, can do it in this way. If you are simply press OK now at the time, this is for go to macro, selecting that, and macros, solver, ports, calculate port extension coefficient. If you are this criteria is not satisfied, if you are construct port from pick face now, that port will form. But in this case, the site is too small. I selected because 0.8 for best performance. So I go to simulation. So we port. So you see, if I do this like this, the port will be assigned to this area. I need to give a port like this area. So select free because I used a big face now, so that's why it will assign the port only to the big surface. So I need to extend this from -4 to 4 because it starts from 3.5 to 3.5, right? So port usually we will increase it from left side and also left side, both the left sides and right side, and also at the top layer. It should it's no need to give it in a bottom layer, and also we need to because if you see the waveguides now, how we give the ports there. There is a big I can show you in the PPT there. Yeah, you see here ports, how we give a ports here. It will be extended up to this and this side, right? So the same way we need to give a port now. Because if you are simply excite in this way, the waves got escaped at this two ends. So I gave it this 4, -4 to 4, and you can also make it as a -2 to 2 also. If you are reviewing this, it will be higher, right? 2.8. Why I gave 2.8? I need to. It will be equal in both the bottom and top. Reviewing address. Okay. This is my port one. Okay. Usually waveguide has two ports, right? Usually my antenna should have only one port because that's a passive device. So output must be radiation pattern. Here it's simply waveguide. If we are uh, shorted at this end also and place a slot at this end, this is act as a slotted SIW. That is a different topic. I made the simple, that is in CSIW concept. It's a basic one to build an antennas for 5G. Okay. Keep in the mind this is not an SIW antenna. If I place a slot at the top only, it becomes an antenna. Because there is no way to escape a radiation right here. Because I made like a room. There's four sides are walls where the EM waves got escaped. No, no way. Then free, the same thing I'm going to place. What is that? Need to do quick face right. Quick face. Now save port 3. Alright. Yes. -4 to 2. Why I select this quick faces or otherwise you need to know about what is X, Y, Z and also this because here X is +11, that plus X is -11, right? So that's why for easy understanding I make this pick face. Now the same thing we need to give here -2 to -2.8. Improper range. What I made here -2 to +2.8, right? 2.8. Yeah, it's a span. Remove it. Okay, this is an actually SIW. This is a port 1 and port 2. port 1 and port 2. Now save this one. Go to home and do dot simulation. And here you can see the ports of excitation. This is port 1. Want to change it now at the time. And this is port 2. What happened? I made a helper. Okay. And after everything, please do check it everything. If you are assigning a ports, if you are doesn't assign the ports now, it came with error. At the time again you need to start. That is, you need to clear all the errors and then again do it. So better you can just cross check it up. What are the things here? Whether you are giving the bottom or that is the stuffs at the top layer is everything is good. Start simulation. So I think here I didn't give a frequency range. It's actually 20, 20 from 20 I said no 20 to 30. 26 because 26 is the range now. 26 to maybe this is 34. This is a minimum and maximum frequency range. You can select it at the first step itself because now I made it in the new one, right? I made some mistake, system crash or otherwise. At first step itself, you need to assign the frequency. Here, the minimum frequency and maximum frequency will be 2.8 to 3.4, so that it will give only the result for 2.8 to 3.4. That's okay. Okay. Yeah. This is what I said. Now there is some restrictions and some drawbacks in student version. This software is licensed for up to 10,000 meshing cells only. So the current mesh sizes exceed the limit, maybe about 10,000. So please reduce the mesh size accordingly. This is what the only error we got. So this is not an error from us. This is an error because we are using this student version, right? So to resolve this error, I will give you a quick solution. First, you need to know the mesh. What is this mesh? Usually, what is this mesh? Because if people are definitely going to work in this student version platform only, that's why I'm explaining this mesh is usually in home we use this mesh for mosquitoes, right? The small holes. This is actually a meshing. If you're considering some part, it's a kind of an integration, you can say. How smallly we can divide that, because if this small place is calculated, the same applies to this place and this place, but this calculation is different from this calculation, right? You can see here. That is what this boxing is about. This box, no, this is actually a radiation box. If you are using HFSS, you need to put a separate box for that. This is what I added advantage in the CST software. When you are assigning the frequency, it automatically put the radiation box. So this small boxes now, this is actually a meshing type. Okay. So if you are meshing too small, the meshing cells became very large. That is after above 10,000. So student version is restricted only up to 10,000. That is what this error says. So we need to reduce this meshing size, not a meshing size, and meshing numbers. The global properties, hexadral. Yeah, there is also the types of, there is a lot of things to explain about this software, but the time is not there, no? So there are different types of meshings is here. So hexahedral, pentahedral meshing is also there. So now we need to select hexahedral hazy, so that here lines per wavelength, that is for per wavelength the lines are 10 lines are there. So lower meshing limit is 5 here. So see here how many mesh cells, it's about 10,000 only, right? So we need to reduce these cells. So please do reduce this number to 6. So if you are updating this now, is 86,940. It's below 10,000. So this error got gone. But if you are giving is as a 7, I think it may increase. See, here 10,000, above 10,000. So you need to give 6 here. Yeah, definitely there is a question in your mind. What is it? What is an effect of meshing? If meshing is too small means this meshing cells is higher, na, we can get a very accurate result for a PhD products and all. That's why I usually recommended a good version, or maybe you may use a cracked version of CST, because this is only for students who are using this. For BE students also, it's okay, because meshing, if you are reducing a meshing, no, at the time your results are not so good. So now start simulation. It's running. It may take time. If you see here, there is some updates here. Okay, and I will say what is this 1D results. There is lot of results here, no? So 1D results. From 1D results, we can able to see S11 and VSWR and all. Okay, and from 2D results, you can able to see the far fields or far fields also. What is a far field actually? For here now, no far field for us, because it's not an antenna. So it is not it's not going to emit anything. So it simply can see S11. See here, S11, that is an S parameters, and VSWR is enough for us. It's still calculating. I'm just showing you. And 2D results contain port modes, and then electric field and magnetic field. How the electric field and magnetic field are aligned inside this SIW. You can see here in animation also. I will show you later after this simulation got over. Okay. Let me discuss about what is this S11 and S22, because this is what the major fault I saw in all the peoples and every papers. No, also including the scopus also, no? Only the IEEE papers are standard. That's why usually the guides are ask us to take only an IEEE paper. The reason is, na, the scopus paper and any other paper, na, their results are not good, because they just like that write the paper, no, without knowing what is the result, how the result really it should be, how it is really it would be like that. No, I will give you an example. This is what we made, right? This is what the result what I got when I done week before. This is actually S11, because we are giving a two ports, right? This S11 and also S22. If my if it is an antenna, it will only gives S11, because I am excited with only one port. As is a waveguide, it contains two ports. Okay. So this S11 and S22 stands for RF and microwave. Also, you can study about the scattering matrices. S11, S22. There is a calculation is also there, no? There's V1, V2, S11, S22, and this S11 stands for return loss. This is the input mode, and this is an output port. Input, output. So my input is also one, my output also one. Means what? How much of a power is reflected back to me? I am feeding at port 1. How much of a port which is reflected back to the port? So in this time only, in microwave labs, we are using isolators there. Isolator is a single direction device, no? Because sometimes the return loss, that is this is so called a return loss. The losses which are written, that is the feed that electromagnetic field which I feed now, that may return back, may affect my system. That's why isolator is placed there in that I think clustron. There is an lab experiment like a klystron, that time there you can able to see that isolated state. So this S11 is a return loss, how much of a power which is reflected back to me. Okay, so here it should be below -10. You can see here it will be -14 also, because my SAW may work from 20 to 40 also, because this wave will come like this. I am shorting my span because of running time, no, I am shorting my span. So my SIW is working for whole frequency, that is 226 to 34. It may work from 20 to 40 also, I'm not seeing that things. Okay, so it should be below -10, means -10 means only a 10 percentage or 0.5 percentage of a power is only return back to me. For example, I am giving a 10-watt power. Okay, usually 1 watt power is we fed it to antenna. If I am feeding 10 watts power, 9 watts power is delivered. That is utilized by my SIW. Only 1 watt power which is reflect back, that is wasted. So in this case only the efficiency come into the picture. If my return loss is below 10 or below 15, if you see here now, this return loss is -30. So at 27 gigahertz, my SAW is working very good, because my S11 is -28 to 30. Okay, so if I fed a 10-watt power, it will utilize a 9-watt power. Only 1 watt is reflected. So no problem for me, because 9 watt is used by my SIW. Okay, the same thing in S22 also. So S22 also I'm just see here, my thing is completed. Port 2. I'm just feeding at this end. Okay. Something I made a mistake. Wait. Okay. I'll let me complete this session. So S11 and S22. So S22 is if I fed it from the second port, how much of an power which is utilized by my SIW is 9 watt. Only 1 watt power is reflected back. So same thing which applies to both the ports. Okay. And again, I actually let's see my S11. If you see here, it's worst. The reason is it's worst. Why I am saying worst? It will work on 20. Here it is working, and here it is working. But compared to this, no, this is not very best. But it is still working. The reason is I made one mistake here. Port 2, no. I'm going to delete this port and bring it in, because the reason is here is my port, here is my endpoint. I made it here. Then how it will give a feed? So that's a mistake I made. So just delete this port. Please do assign the port again. Delete all the results, because we have a time still. Wave port free. Y axis, I need to give it this on Y axis. Why Y axis? Yeah, this is how my port's going to look like. My X axis is -4 to 4, right? 4. This is -2 to plus 2.8. So here I need to define my y position because y position is fixed. So in this here area, you need to select this, then only now you're able to edit this. So this is minus 11. My because my y is here fixed now. If you are previewing plus 11, that is, yeah, okay. Okay, now it's touching. You can see what happened to my cancel. I made something, you can just refer this now. This is what my result actually what I got. Okay, because we have a question and answer session, so that's why I'm winding up. But still we are getting good results only here. You can see the results here. Because of this post assignment is something different here, so I'm not able to do that one. So here I think you people may know about what is S11 now. It should be below minus 10, so my antenna will give an exact results. It should be working from 20 to 38 maybe. And here it's an S21. Yeah, this is the main thing now. What is my S21? This is input and port. Either this is output. This green color and blue color are lying in the same area. So it means my port 1 is excited, output port I get it at 2. This is port 2 it excited, this is input and output. You can you may study it in scattering matrix. So it will ranges from minus 8 to 2.6, maybe to 3. The reason is if this losses is it is in this range, it means the power whatever I gave was at port 1 is transferred to port 2. Okay, means whatever the power I gave it in port 1, it will get it at port 2. That is what it referred as. Same thing, whatever the power I fed it at port 2, it will be get it in port 1. So again, this is a taper session actually. I made it as a taper session. This is different for different people. I made it. Okay, and we made it till this, right? Till this we made. What is this session? This is an actually a transition session. If you are going to connect your SIW with some other devices now, it's a waveguide. So that is a main advantage. We are able to integrate with some other devices also. So we need to make a transition session. So here this is a simple patch antenna feeding. You may see it in the first session, right? This is a strip line feeding. So we made the tapered one, and this is my waveguide. So it becomes a transition from microstrip feeding to waveguide. That is waveguide to microstrip, so that here we can able to connect our SMA connectors. This is actually a taper session. If you are going to put this as in your as a paper or something, if you are having a plan to do this, definitely you need to do this taper session. If you have a doubts, you can ask me. So this is what the taper session what I made actually. It is something difficult one, so that's why I just show it in this PPT one. So here you can see after made it in the taper, my SAW will work on 26 and also in 30, sharp 30. At sharp 30 my SAW is working because I made a transition, right? The transition is on the taper session. Here you can see this is S12. Okay, this is that is in S worst S12. Yeah, again, this is what I came to know. Another parameter is there, that is so called VSWR, that is voltage standing wave ratio. Because if you are designing an antenna na, if you are going with an radiation pattern and S11 and VSWR, it's a simply an waveguide structure, right? So it may have only S11 and that is transmission coefficient. This is in transmission coefficient, reflection coefficient, and also a VSWR. And this is a taper session. After this, the final step after designing is optimization. Optimization is the main thing. Now I am designing it in 1 week before. That's why I give you in an half an hour I gave you a result. No, if you are designing at the first time with the calculation, no, that calculation will only give an appropriate value. It may have some minuses and plus. Example, if my calculated with this 7, I didn't get an result at 7. It may reduce to 6.8 or otherwise 7.5. So it will give just an appropriate optimetric value only. So after designing your antenna, you need to do the optimization process.